if you would recall, yesterday we started introducing more calculus into our calculus class. We started looking at first partial derivatives. We actually found some second partial derivatives as well. I didn't tell you how to do this. You just guessed and it worked out. So one of the things that we did with our derivatives was our primary objective in dealing with derivatives. Find the equation of the tangent thing. Find the equation of the tangent line, or as we saw yesterday, the equation of the tangent plane. We also defined a couple of terms like the vector normal to a surface. When we say normal to a surface, even though the surface is all curvy, normal to the tangent plane, to the plane, tangent to that surface. Here's another thing, what we did with derivatives, both first and second derivatives. We're given a function. We want to find the critical points of the function, and then we want to classify the critical points of the function as a local maximum, a local minimum, or neither of these. So take a look at this problem. Think about how you would use first and second derivatives to get at this problem. We actually don't need second derivatives. Actually, with Desmos, we don't need any calculus at all, but think about how the calculus applies, because getting these points is not the point of the problem. Using calculus is the point of the problem. So take a moment, think about how you would use first and second derivatives to solve this problem. When it comes to classifying, think about how you would use second derivatives. Think about how you could use the first derivative. Think about how you could use the function itself, especially given the simple form of function that we have here. So take a few minutes, work on this problem while we pause the video for some awkward editing. Let's review how to use derivatives to go about this problem. We want to find the critical points and then classify each one as a local minimum, a local maximum, or neither of those. So the first step is find the critical points of f. For this, we need to take the first derivative, set it equal to 0, and solve. That's how we find critical points. So this first task is to solve f prime equals 0. We should also note that we care about where the derivative is undefined, but since we're looking at a polynomial and life is so simple because we're looking at a polynomial, we know that there are no points where this function, the derivative, is going to be undefined. So we're just going to solve f prime is equal to 0. In terms of using derivatives, we want to classify each as a local maximum, a local minimum, or neither, and we have lots of options for classifying these critical points. In terms of classifying the critical points, one strategy is to look for where the first derivative is changing sign. We're looking for where the first derivative changes from positive to negative, because that tells us that the function is changing from increasing to decreasing. That is why we want to find where it's 0, because that's a place, a critical point is a place where the function is possibly, the derivative is possibly changing direction. Therefore, the function is changing. I switched twice and went back to my original incorrect statement. We want to look for where the derivative is equal to 0, because that is a point where the derivative may be changing sign. And if the derivative is changing sign, then the function is changing direction. So where does f prime change sign? Because that would mean that f is changing direction. Another thing that we can do to figure out whether the function is, the critical point is a local maximum, a local minimum, or neither, is to look at the second derivative. What does the second derivative tell us about the function? Concavity. The second derivative tells us about the concavity. So if we've got a point where the function is flat and concave down, what kind of point are we looking at? A local max. And the other one, if we've got a point where the function is flat and concave up, what kind of point are we looking at? a local minimum. If we're looking at a point where the function is flat and the second derivative is equal to 0, what kind of point are we looking at? Are you sure? If we're looking at a point where the function is flat, first derivative is equal to 0, and the second derivative is equal to 0, so we can't determine the concavity. What can we say about that point? I'll do this. So we can't tell, right? Right? I just asked again, so what must the answer be?
Yes.
We can't tell. We can't tell. It could be that it's concave down. It's just really flat at that point. It could be that it's concave up, or not, sorry. There's no concavity. It could be a local maximum that's just really flat. Think about x to the fourth. Second derivative is equal to 0 at 0. It's still a local minimum, right? It's still this. It's just very flat. Think about x to the third at 0. It's neither a local maximum nor a local minimum. So second derivative is a little trickier, but if we get a positive or a negative, now I'm being paranoid. Ever since I switched this one backwards, now I don't know what I'm saying. Panicking. If the second derivative is positive, we could say the function is concave up, local minimum. If the second derivative is negative, we could say function is concave down, and we could determine local maximum. So the other thing we could do is we could look at the sign of f double prime. Because we're looking at the concavity of f. For this problem, we started with a nice simple function. We want to find the critical point, so we'll take the first derivative. Set it equal to 0 and solve. We can get rid of a 3. That'll give us a 3 times x squared plus 2x minus 3. And then we can factor and we can say there are critical points at 1 and -3. These aren't entire points. We usually just list the x values. But here we have the critical points. Next, we would want to classify these critical points, and we have lots of options for this. We could use the second derivative. We could use the first derivative and see where things change sign. Since we know what this function looks like, we could just use the 0th derivative and say that we have since we have a -3 and a +1, we must have a maximum at -3, from your perspective, a maximum at -3 and a minimum at -1, because we know what this function looks like. We have a cubic polynomial with a positive leading coefficient and 2 distinct critical points. So we know what this function looks like. Oh, I was going to use the second derivative as the root, so so we can actually classify these pretty easily just because we know what this function looks like. That would be in service of answering the question, which is never the point, but also why I'm mentioning it. Since we have a cubic polynomial with a positive leading coefficient and 2 distinct critical points, we know what the graph looks like. We must go up, down, and then up again. Because we have two distinct critical points, it must turn twice. Since the leading coefficient is positive, as x goes to infinity, the function goes to infinity. And therefore, as x goes to negative infinity, the function goes to negative infinity. This is just looking at the zeroth derivative. So we can see that there's a local max at x equals -3 and a local min at x equals 1. This is all just based on the zeroth derivative. We know what's going on because of the polynomial. Not reliable to rely on that because we don't always get a polynomial. Also, our polynomial is about to have two variables in it, so. But for this problem, we got that. Let's see how this works if we think of the first derivative, because we're, for some reason, really objecting to taking a second derivative, especially because, you know, later on, we're going to have a polynomial with two variables in it, which means 4 derivatives. You're like, oh, dude, what am I supposed to do with all these? So let's suppose we want to see where the derivative changes sign. So we know what's going to happen here. But if we think of a number line, they were classified using f prime to classify. If I build a number line, I have two critical points at -3 and at 1. We know that the first derivative is 0 at these points. Now we just need to check whether the first derivative is positive or negative in each of these 3 intervals. So using the first derivative to classify critical points means looking at the sign of the derivative in all those intervals. So if I pick something in here, say 0, I can just check f prime of 0. For 0, it'd be easier to use the standard form. Why didn't I do that? Was thinking ahead. That was way too much writing to find out that the first derivative at 0 was negative. So f prime of x is negative. So f of x is decreasing. At 0, f of x is flat. We knew that this was going to happen because we knew what this function looked like. But if we didn't have the graph in our heads, this is how we could find out what's going on between -3 and 1. It can't be doing anything else between -3 and 1. Otherwise, we would have seen a place, another critical point, somewhere where the first derivative was equal to 0 or somewhere where the first derivative was undefined. Now I need to check values above and below. So I know 2 is like right here, but let's go with 10. And then f prime at 10. Instead of using the standard form, I'm going to use this factored one. 3 doesn't actually matter, but 10 minus 1 is positive. 10 plus 3 is positive. So whatever this is, it's positive. So f prime of x is positive. So f of x is increasing. If we go down below -3, we also get positive. The two factors are going to be negative. There's 2 of them. So the first derivative, I spelled net positive wrong. How many NEGs are in positive? Oh, that's right, none. So we see that the derivative goes from positive to negative to positive. So the function is going from increasing to decreasing to increasing. And that tells us that we have a local max at -3 because we go from increasing to decreasing. And a local min at 1 because we go from decreasing to increasing using the first derivative to classify. Any questions? Okay. It's been a long time since the first season of calculus, so we have to have like a long last time on calculus. We also want to be able to use the second derivative to classify. Here, we're just going to be plugging in the critical points themselves and checking the sign, hoping that we don't get 0, which means we have to do something else. The second derivative, going to go back to standard form so I don't have to product rule, is going to be 6x plus 6. And now we'll just plug in the critical points. So f double prime at -3 is negative something. So we see that f is concave down. We knew that already. F is concave down. Since f is concave down and also flat, we conclude there's a local max at -3. If we look at the second derivative at 1, we get 6 times 1 plus 6. We get 12, which is positive. So f is concave up. Therefore, we get a local min at x equals 1. Any questions? What am I going to do now? Everybody's like, oh, dismiss all of them? Like, oh, no, there's 20 minutes left. What we're going to do now is I'm going to just do the same question, but with a function of 2 variables. Same question, function of 2 variables. How are we going to solve the problem? Probably some variation of the same thing. Find the critical point. Set the first derivative equal to 0 and solve. Oh, wait, there's 2. Plug into the second derivative to check concavity. Oh, wait, there's 4. I'm sure you'll figure it out. So, same question. But with f of xy equals, I wrote it down on the sign-in sheet, then I handed the sign-in sheet out. So fortunately, I took a picture. 8y cubed plus 12x squared minus 24xy. Oh, this is the one I stole from the book. So convenient. Think about what your plan is going to look like. And you can see that I pulled out the cards. So we're going to break into groups according to the different boards. And we're going to try to figure out this problem. this problem that I did not tell you how to do, because it's a function of two variables, and I want you to optimize it. And you're like, oh, dude, how can you be asking us questions from chapter 15 already? Well, what can I say? I'm kind of a jerk that way. Good news is, you already knew that. And also, you already know how to solve this problem. All right, split up into teams, and the boards are labeled 4 through 10 along this side. For some reason, I ignored that wall. Find the critical points of this function of two variables and then classify each one as a local minimum, maximum, or neither. You can do anything that you want, but think about first and second derivatives.